Hey guys, I'm Mark. I'm a second year electrical engineering major here at UCLA, and I'm a tutor for Tutorfly. And today we're going to be going over some review for AP Physics C, electricity and magnetism. Alright, so first we're going to go through an overview of what we're going to cover this session. So the first thing is the format of the actual exam, and then some key terms, formulas, and concepts, and then tips and tricks from my own personal experience and from what I've heard from others. And then we'll go through a couple practice problems from the free response section. So the exam format, it's split half and half between multiple choice and free response, and each section is 45 minutes long. The multiple choice is 35 questions, and so that goes by really quickly when you only have 45 minutes to do 35 questions. So we'll go through some tips for how to get through at least most of the questions, and then free response is only 3 questions, but each question is pretty long, so we'll also go through some tips for getting through those as well. So starting off with some key terms and formulas, the first topic that you guys cover in this class is electrostatics, and so the main formula for this is Gauss's law, and so this law can help you solve a lot of problems, and typically there's at least one free response covering it, so it's pretty important to have it nailed down. And so the actual statement of Gauss's law states that the electric flux through a Gaussian surface is proportional to the charge enclosed. And so basically what that means is if you have any surface that you draw in some distribution of charge and you calculate the flux through that surface, which is the surface integral of E dot dA, which you can see there, it's going to be equal to the charge over the permittivity of free space. And so you usually use this for calculations when you can take advantage of symmetry in the problem. So that could be like a point charge or a cylinder of sphere or a cylinder of charge, or a sphere of charge. So things like that where you have a certain symmetry. And so there's an example. With a wire full of charge, you can use a Gaussian cylinder. So that way you can just look at the side and look at the flux of the electric field through one side. Alright, and then otherwise, if you don't have that nice symmetry, so let's say you have like a finite wire or like a ring of charge, then you have to use Coulomb's law, and essentially you just sum up the contributions that each portion of the charge contributes to the electric field. And so that's a little bit more math intensive, but sometimes you're forced to use it. Alright, so the actual definition of charge is based on how much force an object experiences when placed in an electric and or magnetic field. And so that is spelled out with the Lorentz force, and so that you can see here. The force from an electric field is just Q times E. And then for the magnetic field, it's QV cross B. So that's a key formula to have nailed down. So that can basically tell you the force on any charge in any combination of electric or magnetic field. And then just some quick definitions for a conductor. That's just a material through which an electric current can pass. In general, that mainly includes metals. But usually the problem will tell you this is a conductor or this is an insulator or a dielectric. And so a dielectric is a material that does not conduct current, but becomes polarized in response to an electric field. So that usually comes up when you're talking about capacitors. And so a capacitor is just an electronic component that stores energy in an electric field. And so the capacitance you can just calculate with the ratio between the charge stored and the voltage across the capacitor. And so sometimes you'll have to do calculations of the capacitance of a certain geometry. And so the way you do that is you look at how much voltage is across the capacitor when a certain amount of charge is applied, and then you just divide those two to get capacitance. Alright, so the second portion of what you cover in this class is electric circuits. And so a circuit is defined as basically a path through which a current can flow. And so it's basically just a combination of wires with resistors or capacitors or inductors, which I'll talk about later. And the real law that you need for circuits in this class, at least, is just Ohm's law, and that just states that the ratio between the voltage across the resistor and the current is equal to the resistance. So that's just V equals IR, or I equals V over I, R equals V over I. And then when you're talking about an RC and RL circuit, you usually can talk about it in terms of the time constant. And so that is basically a measure of how long it takes the component to reach 1 over E, or 63% of its maximum value. So that could be like the charge on a capacitor or the current through an inductor. And so for an RC circuit, it's equal to the equivalent resistance times C, or L over the equivalent resistance for an RL circuit. So we'll go through some problems covering that later. Alright, and then the last portion is about magnetic fields. And so one of the main laws you use to solve for magnetic fields is Ampere's law. And it's basically an analog of Gauss's law, but for magnetic fields. And all that states is that the integral of the magnetic field around a certain path is equal to the current enclosed. And so that's formulated there. So instead of drawing a Gaussian surface in this case, you draw an Amperian loop. But they're essentially the same thing, just two different sides of a coin, basically. So this you can use to calculate magnetic fields when there is symmetry, just like Gauss's law. And then when there's not symmetry, you have to use the Biot-Savart law, which is a pretty long equation, but it's typically not terrible to solve. You just have to integrate the contributions of each small part of current. So it's basically the same as Coulomb's law, but it's the magnetic field version of it. Okay, and then the next definition is magnetic flux. So that's the amount of magnetic field passing through a given area, and it's calculated by basically doing B dot the area. So it depends on if the area is perpendicular or parallel to B. So as you can see in the picture, if it's perpendicular, it's going to be a maximum value of B times A, and then if it's parallel, it's going to be 0, because their dot product will just, since they're perpendicular, it'll be 0, and then there's angles between that as well, and you would just use the cosine of the theta between the two. Alright, and then Faraday's law, this is what you use whenever you have like an induced EMF. And it states that a changing magnetic flux through a loop induces an EMF in that loop equal to the rate of change of the flux. So that's stated here. So one example is a coil of wire that you move into a magnetic field. So as you move it in, the flux is increasing, and so it would induce an EMF in the wire. The direction of that EMF depends on Lenz's law. So that basically just states that the induced EMF will create a magnetic field that opposes the change in flux. So like for this wire, since the flux is increasing and the magnetic field is out of the page, it's going to want to create a magnetic field into the page. And so the induced current will go in a way such that it creates a magnetic field that is opposite the original one. Yeah. And then here we define inductor. So I mentioned it earlier, but it's basically the analog of a capacitor in that it can store energy in a magnetic field instead of an electric field. And you can calculate inductance by finding the flux per unit current and then timesing it by the amount of loops in the inductor. Alright, so that's it for definitions. So these are some tips and tricks that I could think of based on my experience taking the exam. So like I said, there's a lot of multiple choice questions and not too much time. So if there's a certain very difficult question that you're really stuck on, you can definitely just skip it. It's only one out of like 35 questions, and it's not worth spending 5 minutes on a question if you can finish like 5 other questions in that same amount of time. So have that in your head while taking the test. And then if you end up running out of time, make sure you don't leave any questions blank, just because you don't get any penalty for guessing. And so if you have like 10 unanswered questions and you guess on all of them, you'll probably get at least 2 right. So you should always do that. Make sure when you're answering the free response section to write down key formulas and equations. Even if you don't know exactly how to solve the problem, they'll usually give you partial credit for at least identifying like what formula to use, or or at least like getting the right equation down, even if your final answer isn't exactly correct. And then make sure you're not like memorizing every single equation, because they give you a pretty long equation sheet. So a lot of the times if you're stuck, you can look at that for reference. And then the best way to practice for this test, I think, is to work through actual practice problems and then check the solutions. So there's a bunch online from past years. And make sure you're actually like working through them on your own first and then looking at solutions, because that way you get to know what you don't know and you can kind of struggle through. And then when you get to the actual test, you'll be more prepared for if you get stuck or if you have a certain problem. So that's how I practiced, at least. And then lastly, the nice thing about this test is the average is always super low. So you only really have to get 40% of the points to pass. And so it may seem like you didn't do amazingly when you walk out of the test, but since everyone kind of feels that way, and it's graded on a curve, they're usually pretty generous. So that's the nice thing about the physics test, at least. And then for the free response section in particular, you have to pay attention to the wording of the question. So they'll kind of give you hints based on what verb they use in the question. So for example, if they say justify or explain, you need to support your answer with prose or equations or calculations or graphs. And so you can't just write the answer and expect full credit. If they say calculate, that means they want a numerical answer. So it'll be like some number followed by units, so don't forget those. If they say determine, that basically means you can write the answer down without having to show work, although I usually showed work anyway just to get my thoughts out. If they say derive, that means they want an algebraic answer, so you leave it in terms of variables instead of an actual number. If they say sketch, that is different than plotting. So sketching, you're basically just drawing out the general form of the graph, and then plotting, you actually have to use data points and then basically draw the function from those data points. So there's some examples in the free response. Alright, and then just some quick tips for getting through the multiple choice quickly, just based on physics. So whenever a question asks for electric or magnetic field, this applies to free response too. You should always first try Gauss's law or Ampere's law, respectively, because it saves you a lot of time rather than going through the whole calculation of the other equations. And typically, for free response at least, they'll usually tell you like, oh, you can use Gauss's law, but multiple choice, they sometimes won't mention it, so you have to like be able to recognize that that's what you're supposed to do. Alright, and then for circuits, if it's an RC or an RL circuit, you know that it always follows an exponential pattern. So whenever they ask you to sketch or plot like the voltage or the current or the charge, it's basically always going to follow like an asymptotic behavior. So it's going to start at one value and then finish at some asymptote and then just have like a nice curve to reach that point. So there's some examples we'll do, but that way you don't have to like actually derive the equation for it. You can just know that it's going to be something like this. And then memorize the right hand rule so you can quickly apply that during multiple choice, at least, because they usually ask for like the direction of something. So if you know the right hand rule, you can like quickly find a magnetic force direction or the induced EMF, things like that. And then lastly, remember that magnetic fields can't do any work. So there's, at least all the tests I've looked at, there's always a question that's like, how much work does a magnetic force do? And the answer is always 0, because it's always perpendicular to the path that the object is traveling on, so that means it can't do any work. So that's like a really quick question that you can breeze by. Alright, so now we're going to do some practice problems. We're going to start off with an electrostatics practice problem from the free response. This is from the 2013 test. And so this one is basically an application of Gauss's law. So you're given this cylinder which has a uniform charge density of rho, and it's basically the first two parts are asking you to find the electric field for the region inside the cylinder and then for the region outside the cylinder. And this is an infinitely long cylinder, so that basically tells you can take advantage of the symmetry of the situation. And so the problem actually tells you to use Gauss's law, so that was pretty helpful. So the first thing when you're doing Gauss's law is to determine what surface you want to use. So in this case, it makes sense to use a cylinder since it's cylindrically symmetrical. And so for the first region, you're basically going to draw a cylinder like this. And it has some radius, little r, so that's going to be your distance away from the axis. And so the formulation for Gauss's law is just going to be the flux through the surface is equal to the charge enclosed over epsilon naught. And so in this case, you can pretty easily calculate the flux because you know, just based on the infinite length of the cylinder, you know that the electric field is always going to be pointing out like this. And then on this side, it's going to be pointing out like this. And so there's no flux through the top or bottom of the cylinder, it's all through the side. And so you can basically just say E times the area of the side equals charge enclosed over epsilon naught. And then to calculate the charge enclosed, you just take rho and multiply it by the volume of the cylinder. So I'll do that over here. So that equals rho times volume of the cylinder is just the area times the length. So let's call this L. So it's going to be pi r squared L. And so you substitute this in here. You know that the area of the side is going to be 2 pi r times L, so the circumference times the length. And so you get E times 2 pi r L equals rho pi r squared L over epsilon naught. And so you get some cancellations here, so L with L, this R with one of these R's, pi with pi, and then in the end you get E equals rho R over 2 epsilon naught. You're good. So that's part A. Part B is just asking for the electric field outside of the cylinder. And so you can draw another surface. Looks like this. It's basically a larger cylinder. And you know that the flux is still going to be integral E dot dA. That's going to equal the charge enclosed. In this case, the charge enclosed is going to be the volume of like this inner cylinder, because there's no charge in this region, no charge in this region, just in this region. And so it's going to be, instead of little r here, we're just going to use big R, because it's the whole big cylinder. So we can write that here as rho pi r squared L over epsilon naught. And then to calculate this integral, we know that E is still always going to be pointing out like this. And so we can just use, again, the area of the side. So that's going to be 2 pi, and then this is little r. So it'll be E times 2 pi r L. That equals this. So this cancels, this cancels, this cancels, this cancels, and we end up getting that E equals rho r squared over 2 epsilon naught little r. Alright, and then part C basically just asks to sketch the electric field as a function of the radius, and so we do that really quick here. This is r, big R, 2 times big R. So within the cylinder, so if r is less than big R, we know that it's just going to be a linear relation with little r. So we can just draw a straight line here. And then outside the cylinder, it's going to be related to 1 over r. So that's going to look something like this. And since it said sketch, we can just leave it that general. But we should make sure to label this point. So if we plug in big R to either of these, we're going to get rho r over 2 epsilon naught. And we know this axis is E, this axis is R. Alright, so for the next part, instead of asking for the electric field, it asks for the voltage. And so an easy relation between the voltage and the electric field is just that the voltage is the integral of the electric field with respect to distance. And so in this case, we can just calculate it as V equals the negative integral of E dot dr from 0 to some radius r. And this is given on your equation sheet, so don't stress too much about memorizing it. So in this case, from part A, our electric field within the cylinder is rho r over 2 epsilon naught. And so we basically just substitute this in here, calculate the integral, and then we're done. So V at some radius r is going to be equal to integral 0 to r rho r over 2 epsilon naught dr. So all these are constants, you can just ignore them basically, and then this r is going to become r squared over 2, so we get rho r squared over 2 times 2 epsilon naught, so that's rho r squared over 4 epsilon naught. And so this should all be negative, negative, negative. And then it asks, is the voltage at the outer part of the cylinder greater than or less than the voltage at 0, so on the axis? And you can tell if you plug in an R of whatever in here, it's going to be some negative number, but if you plug in 0, you just get 0, so you know that the voltage at 0 is going to be greater than some negative number, so it's greatest along the axis. Okay, and then lastly, part E basically asks if this cylinder was conducting instead of an insulator, what would the electric field look like? And so basically for a conductor, all of the charge is going to reside on the surface, and the electric field inside a conductor is always 0. And so in that case, you'd have, if you plot the electric field with respect to R, you know that up until big R, the electric field is just 0. So you plot this here, it's going to be 0 up until big R, and then all of the charge is going to be on the surface. So let's say you have rho times this volume amount of charge. It's basically going to jump up to the same electric field that we had here. So it's going to be rho big R over 2 epsilon naught. And then since it's basically the same, if you're looking at it from the lens of Gauss's law, since the same charge is enclosed within this cylinder, the electric field has to be equal. And so from part C, we know that the electric field should look like this for outside the cylinder. And so that's your final plot for the electric field. For problem 2, we have another Gauss's law problem. But in this case, we have a slab that is long enough and wide enough that you can treat it as an infinite slab of charge with a uniform charge density of rho naught. And they actually give you a Gaussian surface in this case, so it's this cylinder here. And we've got a point A and a point B up here. So this is at the top of the cylinder, this is at the bottom. And it's centered right on the origin of these axes. And so the first part of the question is pretty straightforward. It's just asking for the direction of the electric field at A and B. And so if you look at A here, you can basically tell, okay, so there's going to be a net positive charge inside of the sphere, or inside of the cylinder. And so on the top here, it has to point out of the cylinder, so it's going to point upward. And then for the bottom, it's the same line of thought, but instead of going up, it's going to be going down. And so that sort of comes also with like having a physical intuition of what the electric field is going to look like. So doing a lot of these problems will help you sort of be able to do that really quickly. So for part B, it's asking for the total electric flux through the cylinder. So basically when you see this, you should automatically think, okay, Gauss's law, that always deals with flux. And so Gauss's law basically states that the flux, so this is the definition of flux, E dot dA equals the charge over epsilon naught. And so this term you can basically just equate to flux electric. And so all you have to do is calculate the charge enclosed in the cylinder and then divide by epsilon naught, and that's going to be your total flux. And so the charge enclosed, you know, is just rho naught times the volume of the cylinder, and it gives you that the radius is r and the height is h. And so you know that the volume is going to be pi r squared times h. So you can just say the flux is equal to rho pi r, should be big R, squared h over epsilon naught. So for part C, it actually asks you to solve for the electric field inside of the slab. And so you can use what you did in part B to do that. So basically you know that the flux, which is this integral, equals this here. So I'm just going to write equals flux E. And so to calculate this integral, you can look at your cylinder, and based on the symmetry, you know that all of the flux is going through the top and bottom faces. None of it's going to go through the side because it's like an infinite slab. So any charge here is going to be canceled on the other side. And so it's going to be the flux through the top, E A, plus the flux through the bottom, E times A, equals this value, let's write it as flux. So A is just going to be pi r squared again, so you get E. So you can basically combine these two, so you can get 2 times E times pi r squared equals this value. So we'll get rho naught pi r squared h over epsilon naught. So we know these are going to cancel. And we're also supposed to solve this as a function of z. And so if you look here, you know that this is going to be, if this is z, then this is h. Then we can see pretty plainly that z is just going to be h over 2. So that means h is 2 times z. So we can plug that in here. So we'll get 2 times E equals rho naught times 2z over epsilon naught. So these 2's will cancel. And our final answer is going to be E equals rho naught c over epsilon naught. Alright, so for part D, they add in these 2 conducting plates here. So this one has a positive surface charge density of 2 times 10 to the negative 6. This one has a negative charge density of the same value. And it basically asks for you to find the point where the electric field is 0 in between these two. And so you know that from these two plates, the electric field is going to be pointing upwards like this. And then within here, basically above z equals 0, it's going to be pointing upward. And then below z equals 0, it's going to be pointing downward. So you know that for some negative value of z, the electric field here is going to be equal to the electric field between the plates, and that's where the E field is 0. And so you basically just need to find expressions for each electric field. We already have the one inside the slab, so I'll write that from part C. So that's going to be equal to rho naught z over epsilon naught. And then for the parallel plates, you can either remember this formula or derive it through Gauss's law again. But for parallel plates like this, it's the same as a capacitor. So the electric field within a capacitor is given by E, I'll call it E plates. It's just going to be equal to the surface charge density divided by epsilon naught. And that's if the surface charge density is the same on each plate, which in this case it is. And so basically all you need to do is set these two equal to each other. So we'll get sigma over epsilon naught equals rho naught z over epsilon naught. These will cancel, so we get z equals sigma over rho naught. And in this case, this electric field should actually be negative, right? Because we want it to be pointing downward. So if we do that, it's going to be negative sigma over rho naught. And so you just plug in these values real quick. Get 2 times 10 to the negative 6 over, and they give you that rho naught equals 1 times 10 to the negative 3 coulombs per meter cubed. So you plug that in here, by my 10 times 10 to the negative 3. And so in the end, that means that z has to equal negative 2 times 10 to the negative 3 meters, which is the same as negative 2 millimeters. And that's your final answer. Right, so now we're going to do a problem related to circuits instead of Gauss's law. So usually there's about 3 topics they tested for response. It's usually 1 Gauss's law, 1 circuits, and 1 sort of magnetic field-like question. So this will be our second topic. And so in this case we have a circuit with a voltage source here, V naught, and then a resistor and a capacitor in series, and that whole thing in parallel with another resistor. And so part A is asking us to just sketch the charge on the capacitor as a function of time. And so initially it tells us that the capacitor is uncharged, so we know at time equals 0, Q is going to be equal to 0. And then basically the way the capacitors behave is that initially they'll act like a short circuit and they won't store any charge, but then as they build up charge they start to not allow any current to flow through, so it reaches a constant value of charge basically because there's no current coming through. And so we know that there's going to be some asymptote that it's going to approach, and we can fill in that value later. But like I said in the beginning, this is always going to follow an exponential behavior. So in this case, it's starting down here and approaching here. So it's going to follow something like this. So it's going to rise initially and then sort of flatten out as it approaches its final value. And the way we calculate that final value is we know that from KVL, Kirchhoff's voltage law, if we do this loop, we know there's no current through here in the final, as time goes to infinity. We know that all the voltage is going to be across this capacitor, and so the equation for capacitor voltage we can derive from C equals Q over V. So therefore the voltage is just going to be, or sorry, the charge is going to be C times V. And so in this case we'll just plug in values. This will be C naught, this will be V naught. And so that's going to be this value here. Let's rewrite that there. And then that's all we need to do for this because it said to sketch. So we just need to label the asymptote and draw the general shape of it. And then part B, it asks for us to sketch the currents through each resistor. And so in this case, since this resistor is all by itself, basically, if we do a KVL of the outer loop, we know that V0 minus I2 times R2 is going to equal 0 always. So that means that I2 equals V0 over R2. So that's just going to be a constant current basically. So if we plot that here, it's going to be a straight line. And then for R1, it's a little more complicated. So basically, initially, this capacitor is going to act like a short circuit. So there's going to be a current of V0 over R1 through it because there's going to be no voltage across the capacitor. So since we know that R1 is greater than R2, we know that that value is going to be below V0 over R2. So it's going to be V0 over R1. It's going to be less than that. And then basically, as we approach infinity, the current is going to go down to 0. So that's going to be our asymptote. I'm going to treat this like an asymptote. And it's going to follow the same general pattern. So it's going to flatten out as we go along like so. And so that's all you need to do to sketch the currents. So if you do enough of these problems, you sort of start to get a sense of like, okay, I know it's going to look something like this. So yeah, any RC circuit or RL circuit, you can always just find the initial value, then find the final value, and then just fill it in to make it look like an exponential, and then you'll be set. So for part C, basically they tell you that the capacitor is allowed to charge completely, so that means that the voltage across it is going to be equal to V0, like we said in part B. And so after that time, they open the switch again, and so the circuit you're left with basically looks like this. You've got capacitor, and then the two resistors, and that's your whole circuit. But now we have some initial voltage, V0. And so it just asks you to calculate the current through R2, which turns out is going to be the same as the current through R1. But the way you do this is you can sum these two resistances up to find the equivalent resistance, and then to get the current you just divide voltage by that resistance. And so the I R2 is going to equal V0 over R1 plus R2, and they actually give you values for these in this part. So it's going to be 1.5 volts divided by 150 plus 100, and so that works out to be 6 milliamps. Alright, and then for part D, it asks you to calculate the energy stored in the capacitor immediately after the switch is open. So you know that the voltage across it in this case is V0, and then just looking at the equation sheet, it gives you that the energy in the capacitor is equal to 1/2 CV squared. And so you can plug in these values. So C is 80 microfarads, V is 1.5 volts, or V0 is 1.5 volts, so you get 1/2 80 times 10 to the negative 6, and then times 1.5 squared, and so you work that all out and end up getting 90 microjoules of energy. And then lastly, it asks for the energy dissipated in R1 after you open the switch. And so basically the way that this circuit works is it's going to dissipate this voltage by sending a current through each resistor, and the power dissipated by each resistor is going to be I squared times R. So it depends on the actual resistance. So you can basically treat it as a ratio, so you know that R1 is going to dissipate a certain portion of the power. That's going to be R1 over R1 plus R2. Right? So that's just saying, let's say the two are equal. That means it's going to have 1/2 the power here, 1/2 the power here. In this case, it's going to be 150 over 250, so that's 60%. But you know that the total energy dissipated, so let's say times this dissipated. And then from the conservation of energy, we know that this is just going to be equal to the initial potential energy stored. And so that's why they have you calculate this first, basically, because then you can just plug this in. And so you're going to get, if you plug in your resistances, you get 150 over 100 plus 150 times 90 microjoules. And so if you work that out, you get 54 microjoules. So this next problem is one of the experimental problems. So sometimes they'll basically give you an experimental setup and you'll have to work through pretending that you collected data or some sort. And it's basically testing your ability to design an experiment and derive results from certain data. So in this case, you're trying to measure the value of mu naught, so the permeability of free space. And the way you do that is by measuring the magnetic field in a solenoid for a given amount of current. So you know you can relate the current to the magnetic field through math and through Ampere's law. So you can either just remember that, or you can do an Amperian loop up here. And so this isn't going to come into handy until part C probably, but if you do this Amperian loop, you know that you're enclosing, right here, you're enclosing, so I enclosed equals N times the current divided by L, and so, or it's just N times I actually. And you set this equal to the integral of b dot dl. And in this case, you're assuming that the b outside is 0 and that inside it's just a constant b. So this is just going to be equal to b times L. And you set that, so this will be mu naught Ni equals b times L. And so b equals mu naught Ni over L. And so this expression comes in handy for the later parts. But the first parts are pretty simple. So they give you this diagram of a pretend lab bench, and they say connect each component so that you form a circuit that you can measure the current through. And so you just want the resistor in parallel or in series with the solenoid, and you want to be able to measure the current. So to measure current, you need to connect the multimeter in series, so you're treating it as an ammeter basically. And so the way you do that, let's say you just feed this into here, and then you need to go through the resistor, and then from the resistor you go into one end of the ammeter, and then the other end you go loop back to the negative side of the power supply. So that's all you need to do for part A. And for part B, basically it gives you two different types of solenoids, and so the first one is more tightly looped and the second one is more spread out, and it's basically asking which is going to give a better measure of the magnetic field. So basically which one is closer to the approximation that we make. So if you think about it, the closer the loops are, the more magnetic field is going to be concentrated in the middle. And since we're going to be measuring the magnetic field here, it's going to be better in the case of the first one than in the second one, just because the approximation is going to be more accurate. And that approximation is what we use to derive this equation. So in this case, you just say, is it 1 or is it 2? And you just check off 1. So that's the first two parts. For the next part, they actually give you some data. So in this case, they're giving it to you in a form of a plot. They might give it to you in a table and then make you do the plot, but in this case, you already have the data here. And so it asks you to use this plot to calculate a value for mu naught. And so our expression earlier was that B equals mu naught N I over L. And so if we solve for mu naught here, we get that it's equal to B over Ni over L. And so if we look at this plot here, we see that we already have, if we take the slope of this line, we get B divided by Ni over L. So we know that mu naught is going to be equal to the slope, basically. So we can take certain data points that the best fit line passes through to calculate the slope. So in this case, I'm taking a value of 76, and then 10 times 10 to the negative 5 Tesla, and then a value of 24 and 4 times 10 to the negative 5 Tesla. And so the way you can calculate slope is you just do slope equals, since it's a line, you just do B2 minus B1 over, I guess I'll call this y, so y2 minus y1 over x2 minus x1. So we can just plug in these values, so we get 10 minus 4, and then all that times 10 to the minus 5, since that's the units we're in, divided by 76 minus 24. And so if we calculate all that out, we end up getting 1.15 times 10 to the minus 6. So that's our value for mu naught. Experimental value is right here. And so the last part asks you to calculate the percent error of this measured value compared to the theoretical value for mu naught. So that's going to be 4 pi times 10 to the minus 7. And they give you this on your equation sheet. So this is mu naught theoretical. And so to calculate the percent error, we do theoretical minus experimental over theoretical times 100, and then take the absolute value. So in this case, if you plug in this for theoretical and then this for your experimental, you end up getting that your error is 8.5%. Alright, and that number is going to vary depending on what data points you picked, but usually as long as it's within some reasonable value, they'll give you full credit. For the last problem we're going to do, it's related to Faraday's law and induced EMFs. This was a pretty tricky problem, so we'll try to get through it and hopefully understand all of it. So basically what we have is a magnetic field going into the board, as indicated by these X's, and then we have a circuit consisting of this resistor and then a bar with mass M and length L that's basically falling. So downward is going this way and there's gravity acting on the bar, and so that's what's making it initially fall. And so part A is just asking what direction the induced current in R is going to be. And so as we can see, if we treat this area as where the flux is going through, as the bar is falling, basically the area is increasing, so the flux is going to be increasing into the board. And so by Lenz's law, the induced EMF is going to oppose that change in flux. So since it's increasing into the board, the induced EMF is going to go out of the board. And so if we do the right hand rule, and the B field is pointing this way, the current is going to have to go in a counterclockwise direction, so like this. And so through R, it's going to be going to the left. Check that off. Alright, so that's when the right-hand rule comes in handy. So now part B gets a little bit more mathy. It's asking for a differential equation describing the velocity of the bar. And so in this case, you're going to use some mechanics knowledge. So I would start off by drawing a free body diagram. And you know that you've got the force of gravity, so that's going to be m times g. And then you've also got a force because you have a bar with a current. So there's going to be some current going this way that's passing through a magnetic field with a certain velocity. So in this case, if you do the right-hand rule, it's going to be I cross B. So I cross B is going to give you a force pointing upward. So that's going to oppose gravity. And so if you write this differential equation, you can just use Newton's law. So the sum of the forces is equal to m times a. And so in this case, the acceleration is going to be downwards. We can define that as positive. So ma equals mg minus the force of the magnetic field. So that by itself already gets you a point, and then if you want to solve for the magnetic field, you have to use the equation that's in your equation sheet, but you sort of have to work with it a little bit. So you know that the magnetic field force is going to be equal to L, in this case, big L, I cross B. And so since these are perpendicular, you just can take the magnitudes. And so you say LIB. But you don't know what I is, so you have to use Faraday's law to solve for that. You basically know it's going to be the EMF divided by R because of Ohm's law. So I equals EMF over R. And then using Faraday's law, you know that the EMF is going to be the change in flux with respect to time. So that's going to be d over dt of B times A. And since B is constant, we don't have to worry about that. The thing that's changing is the area. And so the area is just going to be this length times basically the height here. And we know that the change in height with respect to time is going to be the velocity of the bar itself. So this is going to work out to be BLV. Okay, so if we derive area with respect to time, we'll just get L times V. And so now we can plug this into here. So we'll get BLV over R, and then plug that into there. So in the end, this works out to be LB times BLV over R, and that's going to be B squared L squared V over R. So this is our force from the magnetic field. And so if we plug that in back up here, we're basically going to get that MA, which is the same thing as dV dt. So we'll get dV dt equals mg minus B squared L squared V over R. So this is our final differential equation. And so that's all it's asking for in part B. So for the next part, it asks you to find the terminal velocity of the bar. And so you can actually use your differential equation that you just derived. And basically when it reaches its terminal velocity, that just means the acceleration is 0. So you can set this term equal to 0, and you get that 0 equals mg minus B squared L squared V over R. And this is technically Vt, so the terminal velocity. And so if you rearrange all of this to solve for VT, you get that VT is going to equal mgr over b squared L squared. Alright, cool. So that was pretty straightforward. And then the hardest part of this problem is part D, where it actually asks you to solve the differential equation. So once you take a differential equations course, it's not too terrible, but for high school students who haven't done that yet, it's a little tricky. So you can do separation of variables in this case. So you just need to move everything with a v onto this side and everything else onto the other side. And so let's make it dv dt. We just divide everything by m, so we get g minus b squared L squared v over mr. So to solve this, we basically need to bring everything with a v onto this side. And so an easy way to do this is to factor out this term so that v is by itself. So we get that dv dt equals b squared L squared over mr times, it'll be mrg over b squared L squared. So we see if we multiply these two, we just get back to g and then minus v. And so we take this part, since it has the v in it, and move it to this side, and then move the dt to this side, and then we can integrate each side to reach the solution. So we get 1 over mrg over b squared L squared minus v times dv equals b squared L squared over mr dt. And so now we integrate this side from 0 to v, integrate this side from 0 to t, where these are just some variable. And so this, since it's 1 over some function of v, it's going to be an ln. So we get ln of mrg over b squared L squared minus v. And then since this is a minus v, there's going to be a negative that pops out. And we go from 0 to v. And that's just going to equal, since this is a constant, it's just going to be b squared L squared over mr times t. And so if we plug in 0 and v here, it's going to end up being basically ln of this divided by this, but with v equals 0. So what that ends up being is ln mrg over b squared L squared minus v over mrg over b squared L squared. So the math gets pretty ugly, but it's not terrible. So b squared L squared over mrt. And then to simplify this, we can exponentiate both sides. So that'll lead to, if we exponentiate an ln, we just get whatever's inside. So we get mrg over b squared L squared minus v. And then I'm going to multiply this to the other side. So it's going to be mrg over b squared L squared, and then e to the okay, so this should be minus b squared L squared over mrt. And so finally we just get that v equals, if we move this to this side, we get mrg over b squared L squared, and then 1 minus e to the negative b squared L squared over mRT. And that is our final answer. So if you look at this, just intuitively to do a sanity check at the end, if you just plug in a 0 here, you know that you're going to get 1 minus 1, so v of 0 equals 0, so that's good because it starts from rest. And then if you let t go to infinity, this is basically going to become 0, and so you get v equals this value, which is equal to what you calculated for the terminal velocity. And so both those are good, so chances are your solution's good as well. So it's always good to do like some form of sanity check at the end. But that was this problem. It was definitely one of the trickier ones. So if you can handle that, then you should be good. So that's all I have for you today. If you want to know more about Tutorfly, you can visit our website at tutorfly.org for more info. Thanks for watching.